Okay, now it's working. So we're starting with problem 7.2 V. Let's recall what we... The purpose is to prove the following identity. Determinant of h lambda I minus I plus j is equal to determinant of E lambda I prime minus I plus j. Is it correct? I mean, indices is the same in the problem. Do we have yeah, that's correct. What we already proved, we proved that we have matrices n plus 1. So let's fix some number n and let's consider the following matrices: h I minus j, I j from 1 to n from 0. And we proved that this is equal to minus 1 I minus j e I minus j. Oh, okay, or this. Yes, from 1. And so this could be different ends, maybe. Like here is one and here is another. Or it's equality in ring of symmetric functions. So let's use different letters, maybe. It's better to use different letters here and here. Like the independent statements like one and another. But we proved, maybe it will be easier. We proved this. Okay. And here number of variables is not important. Like it's equality in symmetric functions. So therefore, I do not need to fix number of variables here. Or you could fix if it's easier for you, but it's the same. Like for any number of variables, you have this equality. And yeah, if I minus j is less than 0, it is 0. If I is equal to j, it's 1. Okay. So, and I claim that this guy is essentially follows from this. So we also solved 2b, and let's understand. If you know some linear algebra, let's recall, if you have matrix A, and you have matrix A to the minus 1, you know some formula for A minus 1, right? Like, if it is matrix of Bij, then, and this is matrix Aij, so Bij is minus 1 I plus j, and minor corresponding to ji. Oh, okay, ij is okay, let's write here bgi like this, right? So minor, if you just consider your matrix A11, AN1, ANN, and delete each column and G's row, right? Yes. But okay, suppose that, so in our situation, determinant is 1, so let's determinant be 1, then that's true, okay? But also you can generalize this for any minor. Do you know this statement? Probably you don't know, therefore you didn't solve previously this. So let's now fix any minor of A. Let's say let's denote by A, I, J, I and J some subsets of 1. And so it's like independent statement here, okay. From 1 to n, you have some subsets, it's I, J's minor, corresponding corresponding to so let's say E1 EM G1 GM. And here I mean I only pick this and this, okay? Maybe it's slightly different from here, but let me use this. Like you pick columns, rows with this number, and here columns numbers. Okay? And you get minor, which corresponding to I and J. What can you say about? Do you know any equality where, and suppose the determinant of A is 1. So what should I write here in order to have quality? Ah, you don't know. It's not Cauchy-Binet, it's just like the same, almost the same thing here. So I claim, so we have to use this. Let me claim the following. -1 I plus j, a minus 1 with minus g prime I prime. Where what is g prime is just complement of j. Okay, and the same for I prime. Complement of I. Okay. Let's test this formula. So this is some particular case of this formula. If I is equal, and I and j is one element subsets. Here you have just element, right? And here you have exactly minor transposed, and with -1 I. Maybe this is, sorry, this is not correct. Here it's not. It should be sum of I case plus or minus, it's not, but it's the same, plus j case, okay? Here is this number. And you have I minus j or I plus j has the same parity. Okay? So it's just generalization of this formula for minors of A and A to -1. Yes, like, but it's slightly, okay, let's write Aij is equal to -1 I minus of plus j. Okay, you could write here A minus 1 ji. Okay. Is it the same? I just put I is equal to I, j is equal to j. It's okay. Here's slightly different notation. It's classical notation where you write ij, but in fact you should write here complement of like one ordinary. So it's not really good notation. Here you should write something like this: 1 I minus 1 I plus 1 and the same for j. Yes. 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 No, it's just like generalization. It's not follows. I just want to show you that it's analogous statement. But is it? I mean, it's slightly different because here it's written Aij of -1 matrix, but you can switch from A to A minus 1 and you get this, right? It's like if here it's Bij, here you have A and it's what it says. Okay? So we have this. Yes, but ordinary it's like, yeah. Plus minus, I mean you could put plus, you could put minus, it's the same. It's not important because it has the same parity. I mean, sometimes it's easy, it's convenient to use plus, sometimes minus. For example, because I will use minus, but here you have plus, therefore I wrote plus in order to have the same. Okay, great. Is it clear? I mean, I don't want to prove this now, but like it's some knowledge from linear algebra, you can, but it seems okay, accessible. For example, okay, like you could consider something like lambda, probably if you consider lambda k, v, and consider the corresponding operator, it should be, maybe not exactly, but something like this. It's something with q degree of vector space, if you want to have some advanced proof of this. I mean, in order to prove this, you could also use top skew degree of your vector space. But okay, so we have this equality. Let's use it for this. You have two matrices and with commutative interest, so that's fine. And we can try with interest from commutative ring. So therefore, all these formulas are the same in field and commutative ring. Any ideas what we want to do? So we pick some lambda. We pick some lambda of some, it's not really important of which number, some lambda partition. I want to motivate you that this is just like half of page in McDonald's book, all this stuff. I mean, but it's not really obvious, but anyway. Maybe we can, let's recall that we have some 7b, some strange, like what it has to do with what we want. But how to get from this matrix this stuff? Okay, let's say this is less than p, and this is I don't want to exactly say this. Let's say a number of lambda, as in 7b, lambda 1 is less than equal to p, and lambda 1 prime is less than equal to q. Lambda 1 is number of rows, lambda 1 prime is number of columns, right? Then, and suppose that p plus q is equal to n plus 1, some number. So we consider all partitions in rectangular, in some particular rectangle. Okay? And let me now, how to get this? Is it clear now that this is minor now matrix? Okay? Like we have n plus 1 times n plus 1 matrix, but we consider some rectangular. P is number of rows, Q is number of columns. We consider partitions in rectangular P times Q. No, let's fix this. Let's fix this. I just want to say that let's consider all partitions which are inside rectangular P times Q. Okay? And suppose that P plus Q is n plus 1. So we will use this matrix exactly for n, for this, for sum of this plus this. So I mean, I want to prove this using, I split partitions into rectangular, rectangular they fit. Okay, so now, can you say me which minor of this matrix is exactly this? So let's choose some I is equal to something, and j is equal to something. Could you say me numbers which I should use in order to get exactly this determinant from this matrix? So here, like, k is less than n, okay? But let's recall how this matrix looks like. It's like 1, it's lower triangular, right? Here you have h1, hn, like h1, hn minus 1, like h1. Okay, this is our matrix. But we want this. So all these numbers are in range 1n. Right? Because this. So once again, the question is, could you say me numbers of columns and rows in this matrix to get exactly this determinant? Simple question. It should be a simple question. Hmm? Let's suppose that we have lambda with like this, lambda 1, lambda pair. Some of them could be zeros, okay? But let's fix, we consider partitions with p parts, but some of them could be zeros, okay? It's not a problem. So like we have exactly p p rows and q columns at the same manner, okay? But some of them could be zeros. Like here, 0 means that you have exactly the same as in original matrix. Okay, if it's not, let me write something. Let me say, consider I is equal to lambda I plus p minus I. And here, g is p minus I, where I from 1 to p. I mean, it's just some computational thing. Like now you subtract from this, and you get what? So you have this matrix. You have this matrix. It contains the same functions. All interest here are somewhere here. Now I claim that this is just minor of this matrix. Yes. But we want to use minor, yeah. Therefore, we want to pick minor here. It will be not lower triangular. Yes. You mean that probably it should be here g minus I? But okay, it could be transposed. That's not really. Okay, but well, let's see. Okay, what you get using this? What is minor with these numbers in this matrix? So what is, so this is matrix P times P, okay? This is like H. Let's denote this by H, and this is by E. H ij is equal to something like, it has some interest, Cij less, and Cij is equal to what? Just H with this minus this, right? So it's like H lambda I plus P minus I minus P plus J, right? I mean, our matrix, it has row minus column number, right? But this is equal to what? Lambda I plus J minus I. Ah, you mean, yes, that's right. Let's switch here. Okay. Do I need to switch or not? So let's lambda I plus J minus I get. No, I do not need. That's correct. No, sorry. So everything is fine. No, I do not. I have to use exactly this matrices because I get exactly this number. No? Lambda I plus J minus I. What is written here exactly? What is the problem? So we pick some minor in this matrix, right? And it has exactly this form. So this is exactly minor of this matrix. What is wrong? Why do you think? That's fine. Yeah. Okay. I mean, it's maybe, yeah, you can think completely formally here. So these formulas are just because they are minors of corresponding matrices. This is exactly. Yes, but it's of H. H is non, so H is this matrix, non-inverse. So we have this minor, great. Now let's use our knowledge about minors of matrix and its inverses. What you can say now, so we know that H E is equal to H minus 1, right? Or H is equal to E minus 1. Therefore, can you say me now, it's purely formal. What is equality between, if we consider minor of H corresponding to I and J, it is equal to what? No. So I denote this matrices by this now. H is not series, it's just matrix, and E is just matrix. So, but what you should have here? So, I mean, I want to have some minor of E here. Could you say which one? What is connection between some minor of H and some minor of E? E, G transposed, and with sign, right? So sign is, so H I J is equal to minus 1 sum of I case plus minus sum of J case. This is just because they are inverse to each other. It's like exactly this. Okay? Now, so I already know that this is our first determinant. Let's compute. So what is now the question? What are indices G prime E prime? But we already solved it, it's 7b. Let's recall what is the statement 7b. It's exactly like this. If you have some number grade some Young diagram in rectangular P times Q, then these numbers plus some other numbers, can you say me exact form of them? I mean, I do not have this. N, it's like n minus 1 plus j minus lambda j prime, right? But now it's n, what is, no, it was correct. That's correct, yeah. But now you have to say that, so we have p plus q is n. What is n in those formula? Yes, n is just p. Yes. So here it's, in our setup, it's p minus 1 plus g minus, sorry, lambda, yeah, lambda j prime and g prime, but g prime is simple. So this is e prime, and here this is e prime, and here g is from 1 to q, and g prime is just p minus 1 plus g. So here it's simple. Yes. Here it's, yes, he's p minus 1 plus g minus, but here from 1 to q. It's 7b, exactly statement of 7b. Like, we also worked with Young diagram and rectangular, and we number. And here is obvious. This is obvious because g is just first p, or last p columns here. Okay. Okay. Now, what is the difference between these indices? It's exactly this number, right? P minus 1 plus j minus lambda j prime minus p. Okay, you have p minus 1 plus j, let's say plus I. Let's use here letter I as for rows, right? Plus I minus lambda I prime minus p plus 1 minus j. So but okay, because here this, so we transpose here these rows and these columns, okay? So we exactly get lambda I prime minus I plus j, so exactly what's written here. What's true that here, in fact, this is not correct. Here you have to use like p, and here you have to use q, or some numbers greater than p and q correspondingly, okay? But it doesn't matter. Like, if you consider some number greater than q, or in fact from the step where some of these guys are zeros, they don't impact your determinant. Like, your matrix looks like this. If you have partition lambda, you have block which corresponds to non-zero lambdas, and here you have 1, 1, something like this, and determinant is this times 1. Okay? I mean, so here, this number should be at least, but if you consider rectangular, so this formula works for rectangular p times q, okay? For all partitions in rectangular p times q. You could put here p, here q, okay? But in fact, you have to, like, you should put here lambda 1 prime, and here lambda 1. Number of rows and number of columns in your Young diagram. It's about which determinant. So they in principle, so you could think that they are of different order or of the same order, it doesn't matter. Okay? In principle, they are of different order, but you can add some number and they will be of the same order. Is it clear? Or not? Mm-hmm. Because subtract from this, but you should switch from columns and rows. The last thing, so we're almost done, but only the question about sign, right? About sign. About sign. Yeah, so you have to, I claim that sign should be 1, so sum of these guys minus sum of these guys, let's compute it. The sign is hard. Sorry. Moreover, this matrix is not as simple, so it has sign in itself, but you see in this formula you do not have any signs. Therefore, in fact, here you have like minus 1 of sum ek minus sum gk times minus 1 to the power exactly the same number as here, right? Lambda I prime minus I plus j e lambda I prime minus I plus j. Is it correct? Because in this matrix, it must consist of with sign at is. And the sign here, sign is the same as number of e. So if you have this number of e, you have the same or not the same, or we transposed as well. No, the same. Yeah, we consider this guy and transpose. Yeah. Yes. So it's the same. The claim is that this times this is 1, which is hard. I'm not. Let's check. I hope it will work. The sign is. So we almost get this formula up to sign, okay? But sign should be always 1. And that's really very strange. Probably. Okay, let's see. Is it really 1? So what you can say, I want to say that this number, sum of ek minus sum of gk plus lambda I prime minus I plus j is always divisible by 2, right? This is the claim. Or not. So this is the no. Yes, this is my mistake. Yeah, right. No, this is determinant. You should put all these guys from determinant, right? So what does it mean? What's correct? If you put minus sign inside it's like it's not multiplying in rows and columns, right? It's like yes, but yeah. So the question is now why this is really equal to determinant without any signs. So how? Yes. But it's not a but probably but you could switch some signs to determinant and get the same determinant, you know. If you have even number, then it doesn't matter, right? The claim is that you could get determinant of the same form with even. I mean, it's not contradiction, right? It's not contradiction. Нет, пока противоречия никакого нет. Еще раз. Ну, жаль, что они всегда совпадают. Вот. Что вот с таким множителем они всегда совпадают. Maybe let's compute this guy first of all. What is sum ik? It's just, in this case, this sum ik minus sum jk is exactly number of boxes in your Young diagram, right? Yes? But okay, we didn't fix number of boxes, right? It could be even, it could be odd, right? So now we should consider two cases. Even, now let's say lambda is even, then here you do not have any sign. And the claim is that in this case here you have this determinant is equal to this determinant. Or lambda is odd, then this determinant is equal to minus this determinant. This is the claim. So the claim is if lambda is even, hence this minus 1 lambda I prime minus I plus j ta is equal to determinant without sign. Let's try to understand this. I mean, it's true. if you're okay with all it. What we can, about if lambda is even, then this determinant lambda is even. So you could consider a concrete rectangular, this times this. Here we have lambda, and here we do not know anything about number of rows, of columns. So we have determinant, right? It's like the question is when, if you have some determinant, like this, they're the same. Could you say, for example, in this case, is it? So our matrix looks like this, right? It's like minus, plus, minus, plus, plus, minus, plus, plus, minus, plus. And here it's like, again, 1 minus, and you get what you want, right? So it means that if, but if you have something like this, then it, then it like, so it means that if you have this, you can always, is it true? No, that's something, it should depend on, like this is not, so what you have here, let's say it's like 1 minus E1, E2, like 1 minus E1, 1, 0, 0, but okay, here it's always the same, yes, this is, yeah, determinant doesn't depend on this. Like this matrix is different, but determinant is the same. That's true. Therefore, but is it really looks like this or not? Yes. Yes. So here, these signs are not doesn't matter, right? It seems like this. So these signs are the same. But and here, therefore, here it should always be. And this is strange. But probably this is, but it should be right number. That looks like it. Okay, this is like x. We're almost done. So these guys are not important for determinant. Okay, for determinant of this matrix and matrix without signs is the same. It's like this. So if you have here, you can switch here sign, you get plus, minus, plus, and again 1 minus, minus, plus, minus gives same. And it's the same for even, for odd and even, guys. So therefore, for determinants, this is not really important. Ah, you mean, right, let's check. It's like if you have something like this. No. No, that's like symmetric. But it seems in our answer it depends on number of boxes, which is strange. Okay, let me leave as exercise. Up to sign, we solve this. Sign is always the hardest. Size, figure out sign. Probably it's not completely true. You have to analyze this better. So if lambda, okay, so up to sign is solved. You could think about sign here. Now let's move. So therefore, this is what gives you this. In the previous lecture, you proved this Jacobi-Trudi formula, right? Jacobi-Trudi formula, and this is another its version, and it is not simple at all. Like, for example, you can use this linear algebra trick, or you can prove it directly. Okay, so now let's solve 7.3. Probably here the key point is that, like, your matrix, your minor depends on number of columns and rows in your Young diagram. But okay, so 7.3. I said it in the end of the previous seminar, but there is another combinatorial definition of Schur polynomial. Yeah, and you already know that all these guys is equal to S lambda. Okay, and this is the key point of this purpose. And now you know from the lecture. Is equal to x to the t, where t from the set of semi-standard Young tableau of form lambda. So you fix some. Like this is basis, the basis of symmetric functions. You fix some form lambda, and you consider semi-standard Young tableau. They are like you consider numbers from 1 to here n is number of boxes is like 9, and fill your tableau in such a way that it's strictly, it's strictly increasing in columns and non-strictly increasing in rows. Okay, like you couldn't put here 6 again. On columns you should be it's strict increase, here non-strict. The claim is that this is equal to this, so you could define your Schur polynomial as what is x to the t? X to the t, it's like x, if it is t, then x to the t is equal to x1 squared, x2, x3, x4, x5 squared, x6, x7. Okay? It's like just number of ones, number. And let me remind you the formula from lectures. Yes. Like we want to prove. Our purpose is to prove this. For why that this is indeed Schur polynomial, and for us Schur polynomial is like a determinant over determinant. Yes, like x lambda I minus I plus j. Like that. Divided by 1 drop. This is our definition. And we want to prove from this definition this. Yeah, but you already proved. Yeah, in fact, we studied representation theory. If you forgot that, already forget that we in representation theory course, it's all about representation theory. In fact, this is a character of representation of GLN exactly and of Sn implicitly. Like, it's not exactly character of representation of Sn, but almost. You have Frobenius formula. But for GLN, this is exactly character of corresponding representation, the Schur polynomial. But okay, what I want to say is that S lambda of x1 xn is equal to sum over mu S lambda of x1 xn minus 1, yeah, this corresponds to restriction, x to the degree lambda minus mu, where mu is over all mu of the following form. Yes. Lambda n. N. Like consider a Young diagram in between. Okay. Ah, yes, thank you. Okay. So now let's use this branching, like this is branching rule from representation theory. For example, it corresponds like if you have representation of GLN or Sn as well, and you restrict representation of GLN to GLN minus 1, then you have this exactly these representations. Yeah, exactly. This is character of GLN representation, and this character of the GLN representation, and this is restriction. Restriction, in fact, if you put here 1, so you do for restriction you do not have this term here. It's just like character of restriction is equal to sum of characters of GLN minus 1. For Sn, it's maybe slightly different, but for Sn we will discuss it. For GLN, not, probably. Because GLN is not finite group, at least sometimes finite. How can we use this formula to prove this? Maybe. Let's just restrict. Let's consider restriction by to the end. If you restrict to the like S empty, like let's say S empty is 1. Just define it. And let's restrict to the end. Then you will have some you will get some monomials, right? If you restrict to the end, you will represent your S lambda as sum of concrete monomials. It's very similar to this. Our task now is to construct bijection between these monomials and semi-standard Young tableau, right? So, like, if you restrict from S lambda xn, so you get monomial, like monomials, some monomials, and they correspond to what? They correspond to what? To corresponding to like some lambda, let's say lambda 0 is lambda, lambda 1 up to. I want to explain you that this is obviously simple. So I want to say this is just corollary of this. Okay? Restrict. Мы берем вот этот многочлен, его это ограничивали, это вот эта формула, я имею в виду. Дальше опять с этим то же самое делаем и так далее. Получается, в итоге, когда вы ограничите до конца, здесь получится сумма мономов. Просто каждому пути, там такой будет путь из этих диаграмм, и ему будет соответствовать какой-то моном. So you will have something like this, and it gives you it gives you monomial. Let's construct by monomial semi-standard Young tableau. Do you know some way how to do it? So let's start. So, да, exactly. This is not tableau, but Young diagrams. You have some sequence of embedded Young diagrams. For example, okay, let's consider some small example maybe. Let's say we start from this Young diagram. You should consider when you restrict, use this restriction formula. You first of all consider some sub-diagram of this Young diagram, which is like this. For example, what it should be. Do we have some other chalk? Let's say, so you have like 3 to 1, right? You could consider something in between. 3, 1, 1, for example, right? And then what you want to do? It's our lambda. Lambda is 3 to 1. You have some sub-diagram 3, 1, 1, right? So what? 3, 2, 1, 3, 1, 1, right? And you want to put number which here? 3. Right? Then you consider another one. So like, let's say 2, 1, 1. Okay? It's just a complement. You have original Young diagram and next one, and they have complement. It's not necessary one. It's not necessary one box. It could be some collection of boxes. But in all complement, you put numbers. Okay. Or maybe let's illustrate it here. Here you could consider 1, 1, 1 immediately. Okay. So it corresponds to this, right? Here you put 2, 2. And now the last, so here if you have 1, 1, 1, this is algorithm. We want to form semi-standard Young tableau. Now, so probably I should say carefully here, like if you have 1, 1, 1, I claim that, so in principle you could put like something like 1, 1, 0, but it corresponds to less variables. So you should probably it's like this, right? Okay. So greater than 0. Therefore, here in the last step you put 1, 1, 1, and you get semi-standard Young tableau. Yes. Or maybe transposed. You should have exactly, so if you have 3 variables, you should have exactly 3 steps, right? I mean, no, so yeah, right. No. Yes, it's of 6, right? No. That's not true. I tried to say no. You just can continue doing this stuff. You should consider 1, 1, 0, right? And you put like. One, 1, 0. Again. why I start, why I start from 3? I shouldn't start from 3, I should start from 6. You have 6 variables. Yeah, somehow I see. So this corresponds to true polynomial in 6 variables, okay? Number of boxes is number of variables, right? Like you split number 6 into some stuff, it's number of variables. So you should put here 6, then you should put 5. So what we I said 1, 1, 1, so 5, 5. And for example, okay, let's see. I can put here 0, 0, 0. You get 4. No. Yes, right. So let's try again. Do I have an example? Okay, right. Lambda. So what I want to get, I want to have. Yeah, indeed, I want to have this sequence. N is number of variables, right? Is number of rows. So n is equal to 3. So in our case, if you start from 3 to 1, here you have lambda 0, lambda 1, lambda 2, and lambda 3 is empty. So maybe we have to, so maybe let's try again. 3, 1, 1, right? So 3, 1, 1, put 3 here, right? Then 1, 1, 1, I say, right? That's fine. And yeah, probably I should put here greater than 0, therefore. And 1, 1, 1 is 2, 2. But no, it's not. That's bad. It's not semi-standard, right? Oh, it is. It's something like with transport. So you put. Yeah, we should start from which number should we start, you say? Because like degree of this guy is 6, right? But okay, no, we fix s lambda of n variables, right? What is let's recall what is connection between n like here, right? You fix lambda, number of boxes indeed is degree of your polynomial, and number of variables is 6, right? So here you have 6 variables. If you have 6 variables, right? So okay, you have 3. Again, you have some sequence 3, 1, 1, 1, 1, 1, 0, 0, 0. This is our sequence, okay? Now I want to construct our tableau. Right. Sorry, n is this. It's number of variables. So here you have lambda 4, lambda 5, lambda 6. Yes. the problem with, and lambda 6 is empty. Okay. And yeah, you do not need here this stuff. So therefore, you continue. It could be empty before. It will be empty exactly on this step if we subtract exactly 1 each time, but okay, 1, let's say 1, 1. But anyway, yeah, we can consider, yeah, we could put here 0, 0, 0 anyway, right? So you start from 6, then put 5. You can, okay. You cannot consider this immediately, right? Yeah, therefore it's not working because I put here a wrong guy. But you could consider this, for example, right? Right. Then 1, 0, 0, and then 0, 0, 0. It will correspond to 4. Yes, 4, 3, 2. Okay, great. And you get semi-standard Young tableau, finally. Great. So this is algorithm, how it works. Now, so you just consider some way and put numbers here. Why it will be semi-standard? First of all, it is obvious that it will be increasing on columns, right? Because if you consider subdiagram, you put here the greatest numbers, and again. You cannot put somewhere, let's say there, great number. So it's like obvious. It's obvious that it's column strict. And from these inequalities, or I can write exactly, you have lambda I k plus 1 is greater. Let me write what I want to write. I write lambda I k plus 1 is greater than or equal to lambda I plus 1 k. This is because just of our rule. This exactly means that it is rows, that it is increasing in rows. This means that it is increasing in rows. Any questions? I mean, so this algorithm, it's more or less obvious that it gives you semi-standard Young tableau. So, да. Ну, как по индукции, можно сказать, что на первом шаге, ну не совсем по индукции, ну, да. Да. Moreover, you could get any, so like, it proves that for any monomial you have the corresponding semi-standard Young tableau, but it's also obvious that you could get any. And also, yeah, what you get. Here you have xn to the, exactly xn to the numbers of this number 6, like x6 to the number of 6, and so on. And you could, here 1, but like, generally you get exactly xn to the number n in your tableau. Of not number n. This was a mistake. It's like of number of this number of boxes in Young diagram. Moreover, you could get any semi-standard Young tableau using this way, just considering, because okay, like this sequence is exactly, you could put choosing this sequence, you could get any you could place this, for example, 6 in any. You could put it here, you could put it here, you could put it here. Okay? Like. I mean, you could here get 2, and then you put 6 here. So, I mean, okay, this is. I want to say this is obvious. Maybe I cannot explain it clear, but you have. This is a procedure, and if you think a little bit, you understand that it's exactly. It will give you exactly all semi-standard Kent tableau, and therefore this formula follows from this branching rule. Okay, any questions? Great. So now let's start new seminar. In fact, there is another task in 7.4, but let's skip it. Like the question is, if you define your Schur polynomial combinatorially, if this is your definition, it is not obvious that this polynomial is symmetric, right? Why it's symmetric? It's absolutely not obvious. But there is combinatorial trick which shows that this is really symmetric. But okay. So for today, let's try to solve problem 1a and b, and then maybe we will solve. Next lecture. Let's compute value of your Schur polynomial at point 111, which should correspond to the dimension of representation. And in fact, there are formulas. We will prove one simple one right now, and non-simple is formula 1v. It's called Hooke-Length formula. But maybe we'll prove it next time. First of all, you can say, okay, the S lambda of 111 is equal to number, just to the number of semi-standard Kent tableau. Right? But it's not obvious how many we have. It's not close. It means that in order to find, let's say, dimension of representation, we can just count number of semi-standard Kent tableau. But if we use this definition, we also could compute S lambda of 111 and get different formula which is like Weil character formula, and they give you the same answers, but it's not obvious. But let's do it. First of all, first step is to compute your S lambda on x to the n minus 1. And I want to say that this is simple. Why? Why it is simple? There is some formula, but why it is possible to compute this expression? Maybe let's recall what is Schur polynomial. Let me write. It looks like this: x1 lambda 1 plus n minus 1, xn lambda 1 plus n minus 1. It's determinant of this matrix. x1 lambda n, xn lambda n. This is your S lambda. No, what's happening if you substitute by x1, xn this 1, x to the n minus 1? Let's substitute, I mean, okay. So let's say v of x times S lambda of 1 x to the n minus 1. So what you have on the first column? 1, 1, 1 you have, right? In next, like here, what you have here, you have x2, right? The same column with x2, but x2 is x, so you get x to the lambda 1 plus n minus 1, x to the power lambda n plus n minus 1. Lambda n, sorry. Right? What is in the next column? x3 in the same degrees, right? But x3 is x squared, so you like x squared lambda 1 plus n minus squared, lambda n, and so on. What do you know about this determinant? Let's recall what is van der Monde determinant. Yes, this is but let's recall anyway, van der Monde determinant. So van der Monde determinant is when it looks the same, 1, x1, xn, x1 squared, xn squared, and is equal to product xi minus xj, I less than j. But here maybe, yeah, in order to have van der Monde determinant, you should write it like this. Okay? Now it's van der Monde determinant with these numbers. So therefore you could write as lambda of 1x xn minus 1 is just what? Product of I less than j, x to the power lambda I plus n so you just put some lambda I plus n minus I minus x to the power lambda j plus n minus j. Okay? And divided by ordinary van der Monde. But let's, yeah, so it's equal to product I less than j, product I less than j xi minus xj, sorry, x to the I minus x to the j. This doesn't matter in order, I less than j or j less than I. And here you have x lambda I plus n minus I, x lambda I plus n minus j. So let's maybe common multiplier. What we will have? If I is less than j, so maybe let's say I greater than j. It's not. You could put here any. Then this one is bigger than this one, and then therefore here you could write x to the lambda I plus n minus j from each guy you could get this one. So in which degree? I mean, how many multipliers you have with this? If we fix j, right? You have, if you fix j, you have n minus j plus 1. N minus j plus 1, right? I mean, if j is equal to 1, you have n minus 1. N minus j minus 1. Yeah, so if no, n minus j. If j is equal to 1, you have n minus 1 multipliers, right? Right. If j is equal to n minus 1, you have 1 multiplier. If j is equal to n, you do not have any one. So this is product over. So from each guy you get this. You get product I greater than jx to the power difference is just what? Here you have lambda I, here lambda j. And here also lambda g. Difference is lambda I minus lambda j plus j minus I. Why minus 1? Minus 1, yes. Okay. And here you could play the same game, right? You get, like here you have product over all j's. And here you have product over all j's, x to the j times n minus j, product I greater than j, x I minus j minus 1. Okay. Now I'm not. Let's check what is difference between what is sum. Like what is sum lambda j plus n minus j times n minus j times n minus j over all j's is equal to what? Sum lambda j plus n. Maybe its degree is not correct. It's something different. Lambda j plus n times n minus j over all j. Yeah, so and it should probably be equal to another number if you rewrite this. But anyway, so this is not, so what is written, it's not x to the power n, it's x to this. Okay, n minus, okay, yes. N minus j, because, I mean, yes, and how many of the same guys we have? Like, you have n minus j multipliers with the same, with this the same second term, n minus j. So you have to sum all these guys. Yeah, I just want to compute this over this. It's like x to the power sum of these guys minus sum of these guys. It's like some number. I want to say that it should be equal to something else. Let's switch summation from j from let's sum over n minus j, not j. Okay. So sum like n minus j to j. What you get? You get j times lambda j. So n minus 2j is equal to what? N minus j. It's like the same anyway. Okay, you get some number. No, n probably is not correct. I think n is not correct. Okay, anyway, you get this number. But this number is not really important for what we want. It's like x to some power. Let's compute at 1, 1, 1. How to compute? If you have this expression, like anyway, you have x to the power sum a, which we can compute by this formula, times product over product. Like you cannot substitute and x is equal to 1 because you have 0 over 0, but you can compute limit. And what is, yeah. So limit when x is equal to 1 s lambda 1x xn minus 1 is exactly number which is written here, product lambda I minus lambda j plus j minus I over product j minus I. It will be exactly these guys. Oh, I minus j, it doesn't matter. Doesn't matter. So you get this. This is exactly formula for as lambda of 1, 1, 1. This is dimension of corresponding GLN representation. And this also called follows from veiled character formula. But there is another form. I mean, like it is what corresponds to veiled character formula, but also you have one V, and it's Hooke length formula. You can just write another formula which counts number of semi-standard Young tableau. And it has form which is written there. Okay, so